Hello everyone. This is an introduction to the VanderWaal's equation of state, developed in 1873. This led to the Nobel Prize that was awarded for this in 1910. About 7 to 8 years before the big influenza pandemic that swept the world, about 100 years ago almost exactly. So what this equation is, it's a departure from the ideal gas equation. It has some things that are similar, and the behavior is similar, but it is completely separate. So the relationship, instead of PV equals RT, is P equals RT over V underbar minus B minus A over V squared. So this whole term is new and looks different than the ideal gas, and this departure here from this V also looks different. It's not very accurate. It's not commonly used, but it was important, and it's an important one to study for what it does. It's the first equation to predict vapor and liquid phases. Okay, so there are newer ones that are similar, but newer, let's just say newer. This is still from the 70s, which is before all of y'all's was born. More recent, so newer EOS. There's one that's a little bit more commonly used called the Peng-Robinson equation of state. So PR, Peng-Robinson, EOS. And the nature of this equation is quite similar. It's P equals RT over V underbar minus B. Looks pretty similar to the VanderWaal's equation of state, but things start to differ on this side. Minus A as a function of temperature, all divided by V underbar times V underbar plus B times V underbar minus B. So it's quite an expansion on the denominator in this right-hand term over here. We'll figure out what those parameters later. So A is a function of T, so it's a function of the temperature, and B is a function of T, so it's a function of temperature. And both of the VanderWaal's and the Peng-Robinson are special cases of, drumroll please, P equals RT over V underbar minus B minus V underbar minus eta theta divided by V underbar minus B times V underbar squared plus delta V plus epsilon, where B in principle, theta, delta, eta, epsilon are functions of T. So these more realistic equations are all vastly different than the initial ideal gas equation of state. And so on the following video, we're going to look at what these equations look like qualitatively on some graphs.